Alright, so the next sort of thing we're going to be looking at are combinations. And combinations, let me just abbreviate, well, combinations are really just going to be, wow, that was awful. Combinations are really just going to be subsets of a set, although in, I suppose, more uh, informal language, it will be a choice or arrangement of objects where order doesn't matter. And as an example, let's look at subsets of a particular set. For example, let's look at subsets of A, B, C, D, E. And specifically, let's look at two-element subsets. So I'm taking all subsets of two elements. Well, what are these? They're A comma B, A comma C, A comma D, and A comma E, B comma C, B comma D, and B comma E, C comma D, C comma E, and last of all, D comma E. Order doesn't matter when I choose subsets because that's how we've defined sets to be. But I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 total subsets. Now, where does this number come from? Well, let's imagine that we instead did a permutation first. Let's suppose we first took a permutation of two letters from this set. Well, the total number of ways of doing this would be 5p2, which is 5 factorial. Let me just speed it up, divided by 3 factorial, which is 5 times 4 times 3 factorial, divided by 3 factorial, which gives us 20. But there are two ways of arranging, wow, what am I doing? Of arranging two letters. So I have to divide 20 by the two different ways that I can arrange each letter. So 20 over 2 gives me 10, which is just the number of sets, ignoring the order that we might have chosen the guys in. Let's use a similar sort of idea. How many ways can I find a 3-element subset? Well, there are P5, 3 different ways of finding a 3-element subset, or doing a permutation of this is the number of permutations of 3 objects from 5, but again, when I choose 3 objects, there's going to be a number of ways of arranging those 3 objects. There are 3 factorial ways of arranging 3 objects. So the number of subsets accounting for that any of these 6 permutations of 3 objects gives me the same set is going to be 5 factorial divided by 3 minus, 5 minus 3 factorial divided by the 3 factorial ways that I can arrange those 3 objects. And this works out also to 10. I'll let you do that on your own. So here is the general formula. The number of combinations, this means unordered arrangements of k objects chosen from n is, we write this 2 different ways. One is we write nck just like the npk notation, but another common way of writing this is parentheses with n on top of k. And the formula here is n factorial divided by k factorial times n minus k factorial. Now this piece right here, the green shaded piece, this just comes from NPK. This k factorial piece right here comes from this is really the number of ways of arranging k objects. So we're taking the total number of permutations and then dividing out by the number of ways that we can arrange k objects. Wow, my handwriting is terrible. I thought it was going to be better with this palette. Oh well. Okay. So let's do some examples of doing this. Good, I've got my pen. So example. Well, there are going to be a lot of examples which involve cards. So let me talk about the typical 52 card poker deck. And each card has a suit and a rank. And there is one card for each possible combination of suit and rank. So one card of each combo of suit rank. So the suits are hearts, that's supposed to be a heart, diamonds, which looks like this. There are clubs, which look kind of like this. And then there are also spades, which look kind of like an upside down heart with a little thing on the bottom. And just for your reference, diamonds and hearts get colored in red, so there are 2 red suits and 2 blue suits, or excuse me, black suits. Okay, now what are the ranks? Well, the ranks are, they're the numbers 2 through 10, and then there is a jack, which is, I'll denote by J, a queen, which I'll denote by Q, a king, which I'll denote by K, and then aces, which I'll denote by A. So there are 4 suits, and there are 13 total ranks, because there are 9 numbers between 2 and 10, and then 10, 11, 12, 13 total ranks. And let me just make this note. There are going to be 4 cards of a given rank, and there are 13 of a given suit. Okay. So get this down because this is just a typical thing. If I do problems like this, I'll try to write down, all the information about what's in the 52 card poker deck, but whatever. Okay, so let's look at some examples here. First, in some games you get dealt a 2-card hand, and if you have 2 cards, it's often good to have a pair. So one question is, how many 2-card hands have 2 aces? Well, there are 4 aces, and we're choosing 2. And your hand is the same no matter which way you mix up your cards, so this means that we're choosing k equal to 2 cards out of 4. So we take we take 4, choose 2, which is 4 factorial divided by 2, I am on something today, 4 minus 2 factorial times 2 factorial. We compute each of these things. On top, 4 factorial is, let me write it as 4 times 3 times 2 factorial, so we'll have some cancellation with the bottom. 4 minus 2 is 2, so I get 2 factorial and 2 factorial. One of these 2 factorials cancels out, so I'm left with 4 times 3 over 2 factorial is 2 times 1. 2 goes into 4 twice, so I'm left with 6. So there's 6 possible ways of getting 2 aces. Okay, another question is, in some poker games, you get 5 cards. So let's say how many 5-card hands have all hearts in them? Well, there are n equal to 13 hearts, and we're choosing k equal to 5 in our hand. So the total number here is going to be 13 choose 5, which is 13 factorial over 13 minus 5 factorial times 5 factorial. It doesn't matter if you write the 5 factorial first or last. Now let me rewrite this as 13 factorial over 13 minus 5 gives me 8 factorial times 5 factorial. I'm going to expand out the top to cancel with one of the things on the bottom, but which one should I go for? The 8 factorial is bigger, so it'll probably be easier for me to work with canceling out the 8 factorial. So 13 times 12 times 11 times 10 times 9 times 8 factorial divided by 8 factorial times 5 factorial. 8 factorials cancel out, and I'm left with on top 13 times 12 times 11 times 10 times 9. And on the bottom, expanding out the 5 factorial, I get 5 times 4 times 3 times 2 times 1. Now I can do some cancellation here, and it's going to be pretty ugly. Let me just cut to the chase, though. I could cancel 4 and 3 with 12. 5 and 2 could cancel with 10, but then I've got to still multiply 13 times 11 by 9. You can do that by hand, but that's why we like having calculators in this class. The answer is 1,287. So there are 1,287 5-card hands that have all hearts. Now the third problem I would like to look at is this. I'm just going to set it up, and then you can think about it, and we'll solve it in the next video because I'm running out of time. So let's take a 5-line poem. An example of a 5-line poem is a limerick. And a limerick rhyming scheme goes A, B, B, A, which is the first 2 lines rhyme, and the third line rhymes with the first 2. So these guys rhyme, and then the middle 2 guys rhyme. But generally, the 2 middle guys don't rhyme with the 3 outer guys. So I could ask generally, how many 5-line poems with 3 A's and 2 B's are there? That is, with 3 lines rhyming and then the other 2 lines rhyming. Think about it.